One is what we call the classical image problem. So using the method of images, you don't need to write this differentiation explicitly. That's simple. Okay, let's take first example, then you can understand what exactly I mean by that. Okay. So this is a one way to solve a given problem, an electrostatic problem, where a charge is given and a particular boundary condition is given. Okay? Clear? So that's actually the uniqueness theorem what we done earlier. So you are having a charge on a given surface, or a distribution of charge given somewhere, and there is a boundary condition. Okay? We apply a boundary condition and we are seeing a unique solution exists to the Poisson equation. Clear? Okay, so let's take the first example. So if we are having a point charge in front of, let's take a point charge plus Q. Okay, we'll take just positive charge as a convention above a conductor. Okay, so I should write here the ground here. So it's grounded. Let's take a plane. Okay, let's take a plane. So you are having this as a plane. Okay? So it's infinite in extent. So you think a sheet of paper and it's infinite in extent. Clear? Okay, so it's conducting in nature. Right? So let's put a point charge Q here plus Q here. Okay? So this is a situation given, and I am supposed to figure out what is the electric field at any arbitrary point. Okay? Here. Clear? So you take an arbitrary point and try to calculate what is the electric field in this very situation. You got my point? So you are having a conducting plane and a charge. It's given. Clear? So is a boundary condition given here? Is a boundary condition given? Okay. A boundary condition is given. You are having this plane is actually grounded. Clear? So when this is grounded, this very plane, what does it mean? So it's maintained at a zero potential. Clear? So that means I am having the potential of this plane is equal to 0. So this is a boundary condition. So you are having a charge given, okay, and a boundary condition is given. So you now apply it to the Poisson equation, you will get a unique solution, is it? So that means, let's say I am having a point P here, and you try to figure out electrostatic potential, or from that you can calculate electric field, is it? So our problem is to figure out what is the electric field, let's say at the point P. Clear? Now how to figure out that very field? Clear? Okay, how to solve this kind of problem? Okay, what to do? Okay, so let's say this is a plane. Okay, let's forget about for the time being. This is not grounded. Clear? Since it is a conducting plane, so you are having a positive charge here, is it? So think as a conducting plane. So you are having a positive charge here. What it will do? It will induce a negative charge. Okay, so it will be like this thing. So you will be having a negative charge on the upper surface and the positive charge on the lower surface. Clear? Got my point? So much now? So because of this very charge, you will be having, let's say, negatives here. So on the upper surface, and the positives will be where? So on the lower surface. Clear? So let's say if this is not grounded, since it is a conductor, this plane is a conductor, what is the field inside the conductor?
0.
That is 0. Clear? Okay, so what is the potential? That's constant. Clear? Within the conductor it's constant because field is 0. So if I don't ground it, so you will be having a positive charge here. So these positive charges will create fields on the lower side. So let's instead of writing it above, let's say in front. Okay, let's try. Then maybe you can answer. So you are having this sheet of paper. Okay, a plane. Okay, so you are having a positive charge here. let's say plus q. So on this very side, so you are having positives, clear? So on this side you are having negatives, let's say, because of this very charge. So if you don't ground it, so you will be having field here, is it? So on this very side, so you are having a charge, so it will induce a negative charge. You will be having a positive on this side. You will be having a simply what? A field on the other side as well, clear? But if I ground it, what will happen? So these positives will go, is it? So it will be maintained at now at zero potential. The surface will be maintained at zero potential, clear? So that means the potential inside will be zero. Because as the boundary condition, when you take the potential at the boundary, it has to be equal to zero. Clear? So it means, so this is maintained now at a zero potential. So what will be the field here? So if I am having charge on this very side, so field will not be here. It is zero on this side, is it? Because there are no charges on this very side. Clear? So entire field, what you try to calculate, it will be on this very side. In other words, let's say, so if this is now ground, so it will not be here, so you will be having only field in this very direction. Got it? So if I think it as a plane, like this thing, and the charge is here, so I'll be having only, let's say this is a z direction, z positive, you will be having field non-zero only where? In the z positive direction. Clear? Okay, so now we need to figure out that field. Okay, how to do it? Okay, how to do that? So I need to figure out a situation. Okay, so let's take this plane again. Okay, so you are having a point charge plus q here. So let's draw the electric lines of force. Is it? So what is the charge on this very sheet? The density, charge density is negative because this positive induces a negative charge there, and this is grounded. Clear? So now draw the lines of force. Tell me. Okay, so you will be having, let's say, like this thing. Left, right. It's not actually a straight line, so it will be like this thing. So there will be where? So this is a kind of situation, is it? Is it true? So these are the lines of force. They will start from the positive charge and terminate on the plate, is it? Let's think if this plate is not there, this sheet is not there, what will happen to lines of force? They should start somewhere and terminate on some another charge. Okay, so what I will do, I will take a, okay, instead of solving this kind of problem, I will solve this problem. I will introduce, okay, that's why we call it as an image. Yeah? So I will introduce an image to this very charge here. Let's say this is along z-axis on the same line. Let's say this is actually a distance g above, and let's call this as a distance g prime. Let me induce a charge. Let me take an image charge q prime. Is it? You got my point? Okay. If we see in, okay, let's think intuitively. What should be the nature of this very charge? Let's forget about this plane. What should be the nature of this charge? It should be negative, is it? It should be of the same amount of this much charge, is it? So that you can have this is the line. These are the lines of force. Okay. Clear? So I have extended my surface because this surface is actually, think in terms of, okay, this way, this is an analogy. So you are in front of a mirror. Clear? This mirror you can think, okay, so you think it is the sheet of, okay, this infinite conductor. Clear? A plane conductor. What happens when you sit in front of a mirror? So you create actually a mirror image, is it? But that is not a real thing, is it? You got my point? What is, how far it is within the mirror? It's at the same distance if you are having a plane mirror, is it? You can think this sheet of paper, this conducting plane as a mirror, okay? So it will introduce actually, okay, you think there exists an image charge, is it? But this is a fictitious charge. What we have to solve in reality? Tell me, what do we need to solve? Actually, we need to solve without this thing. Yeah? You are having charge here and charge on the sheet of paper, is it? Okay, I am actually converting this very problem to this very setup, like this. So you are simply converting it to in this very setup. Forget about the sheet of paper or this conducting plane. So you are having plus q and some q prime. Let's say it is g prime. This is the origin. This is g. Clear? So I will try to solve this kind of problem. Subject to the boundary condition. What is the boundary condition? What is the boundary condition? Now tell me. What is the boundary condition? Potential is zero where? On the surface, is it? So if I take this conducting plane, let's say at origin, okay, so that means I am taking, let's say this is the z-axis, clear? So what is the origin? Z equal to 0, x equal to 0, y is equal to 0, is it? So you can think, let's say at z equal to 0, this very plane. So it means my potential at z equal to 0 is 0. Is that true? So that is the boundary condition. So I will try to solve this kind of problem subject to the boundary condition that potential vanishes at origin. Clear? So that will help us to actually to determine what is this q prime and g prime. You got my point? Okay, so what we are trying to, let me put it again. So what we will do, so the way to do it is, so you are having a boundary condition, potential at, let's say z equal to 0, that is 0. So you introduce actually, so this is the first way. You introduce actually a negative charge here at the same distance. What is the positive charge above the plane, is it? Or in other words, you introduce actually some fictitious charge q prime here at some distance g prime in such a way that you get actually the boundary condition at z equal to 0. You impose actually the boundary condition at z equal to 0. You got my point? What we are trying to do? Have you got it? So that's why we call it as an image problem. You introduce actually a fictitious charge in such a way so that the boundary condition is valid. Clear? Clear? Okay, let me give another. Okay, so this is one of the examples. We will solve it explicitly. Let's take two planes. Let's take two. Okay, what is the net charge here? If it is like, okay, so what is the net charge of the distribution? 0, is it? If I take the net charge of the it is 0. So I have introduced an image charge in such a way so that the net charge of the distribution is 0. Clear? If you don't introduce the, let's say, negative charge, think of this sheet here. So there are negative charges. Okay. So this will be of equal magnitude as this much. We'll prove it. Clear? So what is the net charge of the distribution? So there is a charge neutrality. Okay. Now let's take this kind of situation. You are having a plane. Let's say this way. Another plane is like this. So these are two infinite planes. Conducting infinite planes. They are orthogonal to each other. Let's say at x equal to 0, y equal to 0, and z equal to 0. Clear? So and you are having a charge in front of these two planes. Okay. Let's take this kind of situation. So you have only one plane there in the first case. Now how many are here? Two planes. Is it? Okay, now forget about this very plane. Where will be the image charge? So you will put an equal and opposite charge. Let's say if this is distance d, so you will put what? At a distance of d again. Let's say negative charge. Clear? Okay, so now let's assume, let's call this as a d1. Let's take this as d2. Is it? So you will, okay, forget about this very plane. What you will do? So you will introduce actually a minus q charge on this side, is it? At a distance of how much? d2, is it? Of the same distance. Because these planes, you think simply the plane mirrors. So you are having a person, it is in front of a plane mirror. So you introduce a charge, is it? An image, clear? So now tell me, is there a charge neutrality in the system? So what I need to do, I need one additional charge, okay? So I will complete this thing. So about this very corner, I will introduce a plus q charge. Clear? So for this very point charge Q here in front of two orthogonal planes, I need how many charges? How many images? 3 images, is it? So if I introduce my system in this way, okay, forget about now the planes, my boundary condition will be satisfied. What is the boundary condition? Potential on this very plane, it is 0. Okay, so what is this plane? So y is equal to 0. What is this plane? X equal to 0. So we will be considering only two-dimensional plane here, is it? Samajh aaya? You got my point? So if you now calculate the potential at this very point P due to all these very charges, clear? So you will see, okay, what you will see, what is the net potential then? On this very plane, when you have x equal to 0, okay, you then substitute x equal to 0 means this very plane, what you will get? 0. So when you substitute for y equal to 0, okay, so what you will get? Clear? So we'll see these things in detail. Okay, so okay, let's take this kind of situation. Okay, so let's think of a conducting sphere. So we'll calculate step by step all these things. Think of a conducting sphere. Okay, so you are having some sphere that's a conducting in nature, and let's put a point charge positive here. What will happen? So it will introduce negatives on this very side and positives on this very side, is it? If I ground it, what will happen? So all positives will, so it will be maintained now at a 0 potential, clear? So what will happen? So now you are in front of a spherical mirror, is it? Think of a spherical mirror. So where will be the image? So it will depend whether whether the mirror is of this shape or of this shape, clear? So that means you need to introduce a fictitious charge in its image, is it? So solve for that very image. Let's take that image here. Now tell me, so you are having a spherical surface here. Now tell me, is this charge same as this? When you look in the spherical mirror, is the shape same as yours? No, it is deformed somehow, is it? So that means the amount of charge, what you will introduce fictitious charge here, so it will not be of the same magnitude as this thing. Clear? You got my point. So that means you need to, obviously you need to introduce a fictitious charge and figure out how much charge I need to introduce here. So then you solve the problem with this very charge. Forget about this very surface. So this is how we do with the methods of image. Clear? So if you have to solve, we call it as a classical solution. Okay, using simply the image. So it is simply the analogy with the optics. Clear? Okay. So let's solve this very problem first. Then you will see how we use the boundary condition to obtain the various parameters. Okay. Yes? Any question? Huh? Okay, so you are having first is charge plus Q above a conductivity, above a grounded conductivity. So you are having this as a grounded conducting plane. Okay, so you are having a plus Q charge here. Okay. So what I will do, so you introduce, okay, so this is, let's say this is the z-axis. So let's take this as the z-axis. Okay. So that means this plane is where? It's in the xy plane. Okay. So let's choose this plane to be at z equal to 0. So that means it is sitting in the xy plane, but okay, at z equal to 0 point. Okay, so let's introduce a fictitious charge q prime at a distance d prime from this way. So this is z equal to 0. So this is the grounded plane. So there is, so the field, it will be only in which direction? In the upward direction, z positive direction. Okay, so non-zero field is exists on the in z positive. Okay. Clear? So now let's, if you see, this problem has a cylindrical symmetry, is it? Does it have a cylindrical symmetry? Because it is a dipole kind of thing, no? Okay, so you can, okay, so let me draw a cylinder this way. Clear? So this, okay, why it has a cylindrical symmetry? Anybody? Why it has a cylindrical symmetry? What cylindrical symmetry means? If you rotate your system about z-axis, let's say about the axis of this, so it will remain symmetric, is it? It will remain same. So if you rotate this plane, let's say about z-axis, so the configuration will remain same. It will not change, is it? So you will be having the same kind of field. Clear? Field lines will be same. Okay, so starting from here, going here. Clear? So you are having this cylindrical symmetry. So that means I require actually the cylindrical coordinates. So let's say I am interested in the point P here. Okay, let's say it is having the coordinates x, y, z. Okay, I am interested in figuring out what is the electric field at this point P. Is it? So let's take the radius of this very cylinder to be r. So r is the radius of this very cylinder. Clear? So now tell me what are the points, what is the point for this? Okay, so what are the coordinates of this very point? So of this very charge, so what is that? 0, 0, d. What are the coordinates of this very charge? Okay, 0, 0, d prime. Is that true? So these are the coordinates. Clear? समझ रहे हो? Huh? So now let's calculate the potential. So let's take the potential at point P. So let me write potential at point P. Okay, tell me how. So now we'll forget what? We'll forget the plane because it is grounded. Is it true? So we can now forget the plane. So what is our problem? Simply plus q here and some q prime here, is it? You people are getting it or not? Just tell me. So let's calculate what is the potential at this point P. How I can write? Okay, q divided by what is the distance between this point and this point, is it? And then q prime divided by distance between these 2 points, is it? So now let's write that. So it is q divided by, now tell me what is the distance? Anybody? Just tell me. So let's take, what is the distance? X minus 0 whole square plus y minus 0 whole square, z minus d whole square, then root, is it? So distance between the 2 points, so it will be simply x square plus y square plus z minus d whole square. Then I am having a charge plus, okay, q prime divided by what is the distance? So it will be simply x square plus y square plus z minus d prime whole square. Is that true? So distance between these 2 points. Clear? Okay. So now let's use cylindrical coordinates. Okay. So what are the cylindrical coordinates? X is equal to r cosine of phi, y is equal to r sine of phi, and z will be same as z. So there will be no change in z, is it? So now let's write. So therefore, this phi at point P, it will be a function of r. Now, if you write x square plus y square, that will be simply r square. So there will be no dependence on. So let's write rz. So it will be simply root of r square plus z minus d whole square. Have we applied the boundary condition? We are just rewriting the things, is it? Is it true? Have we applied the boundary condition? No, we have introduced a fictitious charge, is it? But we need to apply now the boundary condition. What exactly the boundary condition is it? So what is the boundary condition? So the potential where at z equal to 0 is 0, is it? Tisha, because this plane is maintained at 0 potential, and I have assumed this plane to be where? At z equal to 0. समझ आया? Okay. So let's apply the boundary condition. So the boundary condition is phi of r, z is equal to 0, that's equal to 0. So what it gives me? So it gives me q divided by root of r square. So this boundary condition is valid for any arbitrary r, is it? So because I am considering potential only where 0, z equal to 0. Okay, x and y can be arbitrary. Clear? So, so that's why this is valid for any r. Okay? Plus, so now when I put z equal to 0, it will be simply d square plus q prime divided by root of r square plus g prime square, that's equal to 0. Okay? Just multiply and rearrange the terms. So let me write. It will be like this thing. Okay, so you take this on this side and take this, then multiply it, cross multiply everything. So you put it in this very fashion. Okay, so you will make q square or coefficients of r, you write like this plus. So you put the coefficients of r, then the other term is minus q prime square p square, that's equal to. So I have just rearranged the terms. So put the terms which come with the r and the other terms which don't have r. Clear? Now this equation is true for any arbitrary r, is it? So you are having this kind of situation. So you are having, let's say, ax plus b is equal to 0, and I am saying this is true for any arbitrary x. Clear? So I am not taking. Okay, so you can think. So this okay, when I am saying this is true for any arbitrary x, so it means then this a has to be equal to 0 and b equal to 0 identically. Clear? So in other words, you can say this is actually b into 1, x and 1 you can think as linearly independent terms. So when they are linear, when I am saying they are linearly independent, okay, so that means these coefficients must be equal to 0. So that is what I mean by saying this equation has to be valid for any arbitrary r. So whether you take r equal to 0, you take r equal to 1, you take r anything. So got it? So it means all r's are what? Linearly independent. So that means this thing and the term 1 here, they are linearly independent of each other. It means their coefficients must be equal to 0. Okay?
So
yes?
So if we are saying that Q prime is the mirror image, then it should be equal to Q.
That's what exactly I am trying, because I need to get the boundary condition. I don't know. I have, based on my intuition, I have said it should be like this. Okay, but I have to deduce it from the boundary condition, whether it is exactly the same thing or not. Clear? Okay, so now we'll see it in a moment. So any more confusion? So what I have done here, look here, I have introduced an arbitrary q prime, which I am saying it's actually image of this very charge. So but I need to figure out how much image I am creating. Okay, I have put an analogy of a plane mirror. You are sitting in front of a plane mirror and you should get the same image, is it? Okay, but here in this, okay, I need to get actually whether you are getting the same image or not. So that I will get from the boundary condition. Clear? Okay, so now, so this is true for arbitrary r. So it implies therefore this coefficient q square minus q prime square equal to 0, and simultaneously these are two simultaneous equations, q prime square d square is equal to 0. Now if you look here, so this very term, what it gives me, q is equal to plus minus q prime, is it? Q prime is equal to plus minus q. Clear? From this very equation, what this gives me? So it gives me actually d prime is plus minus. Okay, substitute this q prime here. So just substitute this q prime here in this very equation. Q prime square is equal to q square, so you will get actually d prime square minus d square is equal to 0. So it gives me simply d prime is equal to plus minus d. So now tell me, so what is the physical situation here? So when you are taking the image, should image be on the same side as the charge on the opposite side? So it means d prime, okay, physical thing. So it should be d prime has to be equal to minus d. So this will happen when q prime is equal to minus q. Now look here. Yes. Just take it out. So your problem? Somebody accompany her? What I am getting the physical thing, d prime has to equal to minus d and q prime has to equal to minus q. So that means if I substitute these values in my potential, what should I get the potential at z equal to 0? I should get z at that point, I should get equal to 0. Okay, so now let's try it. So what is the potential? Okay, let me write. So let's try potential. So it is Rz. So that's simply q divided by root of r square plus z minus d whole square minus, now because q prime is minus q, so it's minus q root of r square plus z minus d. So z minus d, so it will be z plus d whole square. Now let's take z equal to 0. So r z equal to 0, is it? So let's take z equal to 0. If I take z equal to 0, what I am getting? So this is 0, this is 0. So both the terms are same, is it? So I got what? So that you are having other solutions as well. D prime is equal to plus d and q prime is equal to. So this will not yield you the boundary condition. Okay? So among that, there is only one possible solution which gives you what? The boundary condition. So what we have figured out? What we have figured out? Potential we have figured out. आप कहाँ खो गई? No, yes. Huh? Okay. So you got it? So now we have got actually the potential of this very situation. Huh? So what we need to figure out? Okay. So now we can write. So this very charge is here. How much is it? So this is d simply. Now it is in the negative axis, so it will be minus d. Okay, so I can write the coordinates here, minus d, and the charge is actually now minus. Clear? Samajh? But this is not our problem. What is our problem? What is our problem? So the problem is only up to this very plane, is it? Samajh? So that means I need to figure out, okay, what is the amount of charge density here? Is it true? So let's first figure out the electric field. Okay, first let's figure out the electric, then you maybe can get the point what I am trying to say. Okay, look at this very potential. Is this potential dependent on phi? In cylindrical coordinates, how many coordinates you are having? R, phi and z, is it? So this potential does not depend on the angular coordinates. Clear? So it means the electric field what you are trying to calculate, that will also not depend on angular coordinates. Samajh aawa? So can you tell me what is the reason for that? What should be the physical reason behind it? So what is the phi angle? It's this. Okay, so you are having, this is the cylinder. So this is actually the phi direction, is it? Samajh? So this is actually a tangential component of the field, is it? Samajh? So what is our z component is like this thing, eh? Samajh? You got my point? Or in other words, the r is like this thing, because r contains both x and y, is it? You got my point? So you are having, okay, now why this component is not there? So you are having two components of the field. One is normal component, another is what? Tangential component. Tangential component is actually the phi component, is it?
Yes.
So now when you look at this very problem, so what should be the tangential component? We know, okay, so this result we already derived. So the tangential component, when it goes across what? A surface which is having a charge density. So it's always continuous, is it? So that means the component, tangential component of field here, that is same as the tangential component below this very surface. Eh? So you are having tangential component on above the surface, that is same as what? Below the surface. But the field below what is? Below the surface is a conductor, is it? Flash of the conductor. Within the conductor field is 0, is it? So that means field above should be also, because if it has to be continuous, so the field what is below should be same as what? What's the above? So that's why there is no tangential component. Clear? So this is the result of a boundary condition again. Got it? Okay. So now let's calculate the field. Okay, but you are having a vertical component. That is the normal component. That's a non-zero thing. Okay? Because why that is okay? So the charge is there. That's not only the thing. Obviously, the charge has to be there. So can you tell me? Okay, applying the boundary condition. Shall normal component be non-zero as well? The reason being simple. When you move from bottom to the top, okay, through a charged surface, so the normal component experiences a discontinuity, is it? So, now the field below is zero, and the field, if it has to be discontinuous, that means field above this very surface must be non-zero. Clear? So this is the application of the boundary condition. So the field here should be non-zero. The normal component has to be non-zero, is it? So समझ Okay. So let's take now the field, okay, for z greater than 0. So it will be simply minus gradient of 1. Okay. So let's apply the cylindrical coordinates. Since there is no phi dependence, so the gradient in cylindrical coordinates is like this thing. There will be actually partial by partial phi that acting on this thing will give you 0. So that's why I am not writing that thing there. So let me simplify here. So you need to now differentiate. So differentiation of this thing with respect to R, differentiation of this thing with respect to R. 2 terms for R, 2 terms for Z. So let me write those things. So this is simple differentiation. So it will be Q R like this. So R divided by R square plus Z minus G whole square. That is called equal to minus R divided by R square plus Z plus G whole square. So this is the R component. Okay, look here. Differentiation of root of R is whatever. So it will be R raised for 3 by 2, is it? So this factor raised for 3 by 2, then differentiate inside. So it will be twice R, is it? So because there will be 1 by 2 coming from the differentiation of 1 by root. Okay, so that 2 will cancel. Okay, and this R is here. Similarly, on that this minus is here. Okay, so now let's write the Z component plus Q times. So this is Z. Now differentiate with respect to Z. So it will be Z minus G. Simply differentiation of this internal differentiation twice Z minus 2 will go. So it will be like this. Okay, R square Z minus G whole square is 2 minus another will be Z plus 2 divided by R square plus Z plus 2G. So you are having 2 components here. Okay. Clear? What is the direction of R here? Anybody? R is actually the radius, is it? Okay. So now let's. So now this is electric field above this Z. So that means it is here. Now let's take at a point which is near to this thing. I mean near to plane, is it? So let's take a limit which is near to this very plane. So that means let's choose okay, Z tends to 0 plus. Okay. So for the Z tends to 0 plus, what does it mean? 0 plus means I am coming from the positive side, and I am going to near the surface. I am very close to the surface, so that's why I am putting 0 plus. So when I put Z equal to 0, so essentially you put Z equal to 0, so this term will go, is it? So what remains there? What remains there? Only this thing. When you put Z equal to 0, so you will have minus G this thing, so minus G this thing. So it is minus twice. Clear? Okay, so it is minus. So the electric field will be simply equal to minus twice QD. So R square plus D square plus that's actually along in the Z direction. So if you see, if you identify what this is, what this field is, it's actually the dipole, is it? So we have, if you see, we are at the beginning, we actually imagined our system as a dipole, is it? Huh? So in other words, this sheet, so you will be having actually an induced negative charge on this very sheet, is it? This sheet and this positive charge, this will form actually a dipole, is it? Samashama? Clear? So Samashama, why negative sign is here? Because why we are in this very case, where exactly we are? We are just near to the sheet, is it? Why this negative sign is there? So the field lines are actually in the opposite direction, is it? So if you are the observation point is here, so the field line moves towards the surface, is it? So the field is actually in the opposite direction, clear? So when you are in this kind of situation, then there will be actually the force of attraction between the charge and the sheet, is it? So this sheet will actually attract. Think of, let's say, you are having a parallel plate capacitor. Okay, one side is positively charged and another is negatively charged. Put a charge within the capacitor. Let's say positive charge. What will happen to that? So that will move to the negative side, is it? So, or you think simply as two metal plates, okay? Or think simply a one metal plate, put a charge somewhere, okay? So this charge will get attracted towards that plate. Is that true? Is that true? Okay. So now let's calculate. Okay, what is the field below this Z? That's equal to 0. Since we are where? We are actually in the neighborhood of this very plane, is it? So we are simply in the neighborhood of the plane. So if I take, so this is actually the field. Let's calculate how much charge density is produced. Okay. So therefore you are having induced charge density on plane. So how much is that? Can anyone tell me? So you are having like this thing, N dot E above minus E below. So this is the boundary condition we know. That's actually equal to 4 pi sigma. And sigma is the amount of charge on the sheet of plane, is it? On the plane, is it? So across we are moving. So now tell me, what is N? N is actually the Z direction. We are moving along the Z direction. Okay. Okay, what is E above? It is this very field, is it? Okay. So it is minus twice QD by R square plus D square raised to 3 by 2. Okay. Along Z direction. What is E below? That is 0. Because there is no field below. So you are having 4 pi sigma. So let me write it as sigma induced, IND. Okay, so therefore, what is sigma induced now? So it's equal to Z dot Z is equal to 1. So it's simply minus 1 divided by 2 pi QD divided by R square plus D square raised to 3 by 2. Now look here. So is this a uniform charge density? Is this a uniform density? Uniform would be constant, is it? Or is changing? So as, okay, now if you stretch out this very radius, okay, if you stretch out this in radial direction, what will happen? Charge density will fall, is it? So that means if you are having a charge just below this very thing, charge density will be large, is it? And charge density, when you move out from this very point, so that will decrease. As how much? 1 by R cube. So let's say if this D is small, that means this charge is just here. It is, just above the plane, clear? At a small distance. So you can, let's ignore this thing. So it will be simply R square raised to 3 by 2. It's simply R cube, is it? So that means charge density when you move out of this very point. Let's say it is at the origin. So when you move out of this very point, it will fall up. Okay? So density about this very region is not same. So it means the density, if this plane is infinite in extent, so that means at the larger distance from this very point, density will be what? 0. So essentially there will be no charge. So it will be actually where? It will be concentrated near the, just below the point where you are having the charge, is it? More charge density there. Clear? Okay, but I need to calculate how much charge is it. It is just the density on the surface, is it? As surface charge density. But I need to calculate how much charge it is. So let's calculate the total charge that is there. So let's calculate. So that means how much charge is created on this very surface. Okay, so I need to integrate this thing over this, I mean surface element. I mean the surface, entire surface. Let's say it is gs sigma x. Okay. So what is the surface we are considering? It is the slant. We are doing it in the cylindrical coordinates. What is sigma of s? It's minus qd divided by 2 pi. So integration over r dr d phi divided by r square plus d square is called. Got it? So since there is no phi dependence, integration over phi is 2 pi, and 2 pi and 2 pi will go. So let me write minus qd by 2 pi. Okay, 2 pi. So what is the integration then? R dr. So you put r square plus d square is equal to, let's say, some z square. Clear? So you will be having now twice z something. So ultimately, once you solve it, this will be like this kind of thing. R square plus d square from 0 to infinity. So it will be actually minus. So what is the differentiation of this big object? It is this object. R dr. Okay, r divided by r square plus d square, is it? With a minus sign. That's why I have put a minus sign. So how much is that? So you put infinity. So it is 0 minus d. Okay, d and d will cancel out. So it will be simply minus. Is it true? So is it minus or plus? Sorry, it is minus. So minus and minus. Clear? So how much is the inducer charge? It is same as minus. So charge conservation is not violated. So charge conservation, because you started with how much charge plus how much inducer charge will be on this plane. So it should be minus. So that's why we are able to actually put a image charge here of the same amount, minus. Clear? Samajh? Okay. So now you are having two charges at hand. So one is the, okay. Yes? Okay, no, look here. Put this as infinity. So first term is 0, then minus. Okay, so that minus and minus will be plus, is it? Clear? Okay. So now you are having actually a positive charge and a negative charge. What will be there? A force of attraction, is it? Clear? So let's calculate how much force of attraction will be there. So for that matter, what we will do, we will simply calculate first potential. Okay, so we'll okay, we'll consider this charge. Okay, if you okay, that's right. So you are having now electric field when you are actually near to this very point. I mean near to the surface. Where is the electric field? It's actually I mean it's along the z direction, is it? So if you are having, forget about this very plane. Now if you are having a charge and the field is along z direction, what is the force of attraction or force of repulsion? What is the direction of the force? It will be along z direction. Clear? So let's say if you put this very charge, let's say here, okay, so it's already along z axis, so that means force of attraction will be along z, direction of the force will be along z direction. Clear? So it means I need to consider the potential due to this very charge distribution. Since now you are in a plane which contains that charge distribution, I need to calculate the potential due to that charge distribution. Where? Along z direction. So you got my point? So I need to calculate simply the the field along z direction only. So You got my point. So you are having this now source, so it will attract this very charge. Yeah? So let's calculate the potential. Okay, here. I mean you can now. Okay. So you are having x equal to 0, y is equal to 0, and z. So that means I am considering the potential only along where? Along this very z direction. Okay, due to this charge distribution. So how we usually calculate the potential? Can anybody? Usually we calculate potential, if you remember. Okay, sigma of s prime ds prime divided by r minus r prime. Is that true? Clear? So that means you are calculating the potential due to this very charge distribution, and you are integrating over which coordinates? Okay, you are integrating the coordinates. Those are defined for the surface charge density. Is it? Okay, now tell me in our case. Okay, first you should understand this. This sigma of s prime, it is defined on the plane. Is it? So what are the coordinates? These r prime coordinates, because r prime is where? It's a coordinate for the surface, is it? So what are the coordinates? Now tell me. Tell me. So where is this surface? It's at z equal to 0, is it? Because I assumed this plane at where? Z equal to 0, that is in the xy plane. So for this very case, I am having this only xy and 0. Clear? So this is our plane. Clear? Now what about this point R? So what is this very point? Since we are considering only it where? Along the z direction. So this point R will be, okay, so I will write this, in our case, this R prime will be simply x prime y prime 0, and this R is simply 0, 0, 0. Clear? So I am considering only the force of attraction along which direction? Z direction. So that means I need to then write this thing, integration over sigma of s prime ds prime, okay, divided by, okay, let me write capital R minus R prime. And why these are the coordinates? So what is our sigma of s prime? So it's minus 1 by 2 pi, okay, qd integration over, what is ds prime? So it will be simply r prime, dr prime, g phi prime, divided by, what is this r minus r? Now let's take this thing. So it will be simply x prime square plus y prime square plus z square. Okay, raised to r. Teacher? In cylindrical coordinates, what I am having? qd divided by 2 pi. So it is, okay, this g phi will give you the 2 pi. So it will be simply r prime gr prime divided by, so it will be r prime square plus z square raised to power 0 to infinity. Oh yes, I have forgot about this very factor. So there is a factor of 1 divided by r square plus g square raised to power 3 by 2. So this is r prime, because I am taking sigma of s prime. So it will be r prime. What is r prime? What is r prime square? X prime square plus, okay, so divided by r prime. So how to solve this very integral? There is an easiest way. So first put, let's say, let's write r prime square is equal to some x. So twice dr prime is r prime, dr prime is equal to dx. So this would be some minus qd integral, okay, 0 to infinity would be there. So let's, okay, forget about the integral at these variables. So it will be simply dx divided by x square plus z square raised to half into x square plus, sorry, not x square, x, okay, and d square. So you need to check it. Okay. So this is actually the way how you can do. So this will be simply natural log of twice. So let me write a result, which is x square plus d square plus z square into x plus d square z square plus twice x plus d square plus z square. Okay. So evaluate it at 0 to infinity. The first term will give the infinite result. Forget about the infinities, because we have encountered this already. So the infinity you can remove. I mean, you can just Okay, ignore the infinity, then you need to take only the finite value and then differentiate it. Okay? So it will be simply minus z plus g. Okay, let me tell you again. So once you substitute infinity, is it? So you substitute infinity. What will be the first term? Log of infinity. That is, okay? So summation one, log of infinity, is it? So first term will be the infinity, is it? Now let's put x equal to 0. So it is 0. So this term is 0. It will be simply d square z square. Okay, twice. So it is something 3 times d square whatsoever. You need to check it. Twice dz, and then you are having d square plus z square. That's simply d plus z whole square. Clear? So you can take out. So it is log of d plus z. Then you differentiate it with respect to d. What is differentiation of log of x? 1 by x. So you get what? Z plus d. Okay, because 2 and 2 will get cancelled. The summation of minus comes up because it is first term minus second term. Clear? Samajh now? Okay. So you have calculated now the potential. So what is now the field? So we are almost done. Okay. So therefore, so if I know electric field along this direction, okay, so it is along z. So let's say at some point z equal to t. Let's calculate it. So it's simply minus z partial by partial z. Okay, of the potential. So that's minus q. So how much is that? So you need to put, okay, so let's calculate simply z. So how much is that? And then find, let's say z. So how much is that? You just differentiate it with q divided by 4t square. Samajh aaya? Clear? So it is the electric field due to what? The plane. At what distance? How much distance we are considering? Z equal to d. So samajh aaya? You got it? So we are considering just the electric field due to the plane at a distance of z. So how much is that? Minus q by. So minus means simply it's a negative charge. Clear? So samajh aaya? Now what is the force? So therefore the force of attraction. So that will be simply q into e. X equal to 0, y equal to 0, and z equal to 3. So how much is that? Simply minus q square over 4